Hello and welcome. In this video, we will be talking about correlation. Correlation is the mutual relationship between two or more things. There is this popular saying that it is in our darkest moment that we see the brightest star. This means the darker it gets, the brighter the stars become. So this is an example of correlation. Let's dive in. We have three types of correlation. These are positive correlation, neutral correlation, or we say no correlation, and we have negative correlation. A positive correlation is established when we have two variables, and then when one of the variables increases, the other is also likely to increase. And when one of the variables decreases, the other is also likely to decrease. Secondly, we have neutral correlation or no correlation. Just as the name implies, irrespective of how one variable is changing, it does not affect how the other is changing. Lastly, we have the negative correlation, which is established when one variable increases and then the other have a likelihood of decreasing when the first variable increases. And then when that variable decreases, the other have a likelihood of increasing, which means they do opposite things. So just as the graph implies, if you look at the positive correlation, you see that when the y increases, the x increases. That is why we are having an arrow moving in this direction, such that when the y increases, the x also increases. And then for the neutral, it means that in this case, we can say the y is increasing, but we are not seeing any change in x. Or we can say the x is increasing and we are not seeing any change in y. And if you look at negative correlation, as the y is increasing, we can see that the x is decreasing. So let's say this is a top point in y, but if you look at it, it is a low point in x. But if you look at this point, it's a low point in y, but if you look at this, it is a top point in x. Correlation is denoted with the letter R, and we have a correlation coefficient that is used to describe the level of correlation between two parameters. This correlation coefficient ranges between -1 to +1, with -1 representing a perfectly negative correlation and +1 representing a perfectly positive correlation, with 0 representing no correlation. In between these -1 and +1, you can have series of values ranging in between them, and these values represent the strength of the correlation. For example, you can say you have a strong positive correlation when you have a value ranging between 0.7 and +1. But when you get to +1, then it is perfectly positive correlation. But let's say something like 0.7 to 0.999 whatever. That is a strong positive correlation. In the case of negative correlation, you have ranging from -0.99999 to 0.7. That is a strong negative correlation. In between that, we still have moderate positive and moderate negative correlation ranging between 0.3 to 0.7 for moderate positive correlation and -0.7 to -0.3 for moderate negative correlation. Between 0 and 0.3, you can say you have a weak positive correlation, but when it is giving you exactly 0, you know that is neutral. And between -0.3 to 0, you have a weak negative correlation, but when it is exactly on 0, you have neutral. So this will be the foundation for what we'll be learning after this. Now, talking about positive correlation, we talk about perfect positive correlation, and when you have perfect positive correlation, one of those things that you will notice is the proportionality in the difference. If the difference between something is 2, 2, 2, 2, 2, let's say 2, 4, 6, 8, 10, 1, 2, 3, 4, 5, if you are looking for the correlation between such variable, definitely you are going to have a perfect positive correlation because the proportionality is perfect. As one increases with 1, the other increases with 2. Or as one increases with 2, the other increases with 3. So that is a perfect positive correlation. But most times in real life situations, we don't used to have perfectly positive correlation. So because of this, we have strong positive correlation ranging between 0.7 to 0.9999, just like that. So when one increases, the other will also increase. When one variable increases, the other variable will also increase, and the proportion will be almost perfect, but not exactly perfect. But if you draw the graph, you are going to see that most of the data points, the midpoint between the x and the y, you are going to see that is going to align closely to the best line of fit. This straight line here is called the line of fit. So when you look at this, it's almost aligned. Same with this, same with this, same with this, but not like this, where everything falls on the line and everything is perfect. So we also have weak and moderate positive correlation. In this case, there is a level of randomness that is more than what we have in strong positive correlation, but you may notice that, okay, when one increases, the other decrease. When one increases, the other increase. The increase is not something you see after looking at 5, 10 data sets. It's after looking at a lot of data sets, and the R value can range from 0.1 to 0.69. Now, look at this graph. This we have here is what we call the correlation matrix. So when you want to study the correlation between many things, you want to look at how many things relate with each other, you use the correlation matrix. Now, what are the components of the correlation matrix? Normally, you have the row and the column. So, and then you have your correlation, your R value inside the cells. So, one thing you will notice with all correlation matrix is that when you look at A and you look at A on both the row and column, you see that the correlation between it is 1. If you look at B and B, you see that the correlation is 1. C and C and C, you see that it is 1. Then D and D, you see it is 1, because the correlation between a data set and itself is always 1. So that's that. Then another thing to note is that, talking about proportionality, if you come to this table here, look at A, look at B, look at C. What is the difference you notice there? This is A, 1 to 7. This is B, just like saying we multiply A by 2, and we have 2, 4, 6, 8, 10, 12, 14. So this is C, we have A in multiple of 3. 3, 6, 9, 12, 15, 18, 21. So because they are perfectly proportional, what do we have here? The correlation between A and B is 1, A and C is 1, B and C is 1. So if you look at D, what happens? I just try to mix data set between B and C. I just try to mix it in D, such that there is an increase, but it is not perfectly proportional. But it is still a strong positive correlation because it aligns well in many points. So look at this. You have 0.975. This is a strong positive correlation between A and D, B and D, and C and D. So because A, B, and C are proportional, so the correlation between them and anything would also be the same. Now, talking about negative correlation, this is just like the opposite of positive correlation, with every other thing like remain constant. So perfect negative correlation, -1, that's the R value, and then it aligns perfectly, and when one increases, the other decreases, but in a perfect proportion. We are going to see an example for this in the next slide. Then we have a strong negative correlation, not really perfect. The proportion is almost perfect. So the R value cannot be -1. So it ranges between -0.99 to -0.7. So here we have moderate and weak correlation ranging between -0.69 to -0.1. And when one increases, there is a net decrease recorded in the second variable over a long period of data, and then you have it to be very random, just like moderate and weak positive correlation. So here we have the correlation matrix, and one thing you should note here is that because these are negatives, does not really mean that if you place this against itself and find the correlation that it will give you -1. No, because the data sets, any data set with itself, when you find the correlation, it is always 1. So that's why when you have -b against -b, you have 1. -c against -c, you have 1. E against E, you have 1. A against A, you have 1. Now, take a look at this. You have a perfect proportion, but it is negative. So because of that, A against -b is -1. A against -c is also -1. -b against -c is 1, because if you look at this data set, -b has negatives, -c has negatives. The proportion is perfect, such that if you multiply every of these by 1.5, you have the exact thing you have here. So definitely they are perfectly proportional, and then the correlation between them is 1. And then if you look at A against E, because it's not about the number, it's about the difference. So what I just do here is, I think I just reverse what we have as D in the other slide, and I arrange it from top to the bottom, instead of like from bottom to top, instead of top to bottom. I just flip it. So because the difference is still exactly the same, just that the difference is just, instead of increasing as it go down the row, is decreasing. So what I just have here now is A against E to be -0.957, and same with B and C. Yes, we can have a data set that have no correlation, and these are the representations for that. The R value is 0, there is no relationship, it is very random. As X is increasing, you will not even notice any increase in Y, or as Y is increasing, you might not even notice any increase in X. These are few examples of correlation. So what I want to do now is pause this video, take a sheet of paper and write out, is it positive correlation, is it negative correlation, or does it have no correlation? Now let's do this together. I want to believe you are, let me give you 5 seconds to pause the video. Yeah, I want to believe you are done. Now, so the darkness of the day or night mean the darkness of the environment, and the brightness of the star, is it positive correlation or negative correlation? It is positive correlation, because we say that it is in our darkest moment that we see the brightest star, which means that the darkness of the day or night is positively correlated with the brightness of the star. Secondly, we have the time on treadmill, which is the time used to exercise on the treadmill, and the calories burnt. So is it positive or negative? The time on treadmill, which is exercise, and the calories you have in your body is negative. But the calories that you burn is positive, because the more time you spend, the more calorie you burn. So positive. Slimness of a person and their tendency to have obesity. So when someone is slim, do they have higher tendency of obesity or lower tendency of obesity? Definitely lower tendency of obesity. So that is negative. Now, the fatness of a person and their tendency to have obesity, and that is positive. Hours of work and hours of free time. The more you work, the less free time you have, and the less you work, the more free time you have, which means as one increases, the other decreases. So therefore, that is negative correlation. Next, we have color of shirt and level of intelligence. An intelligent person can wear the same shirt as a dumb person, and a dumb person can wear the same shirt as an intelligent person. So as intelligence increase, it's not as if as intelligence increase, there is a color of shirt that people tend to wear when they become more intelligent, or there is a shirt that people wear when they become less intelligent. No. So therefore, these are not even related at all. So we can say this is neutral, no correlation. So thank you for watching this video. I hope you learned a lot from this video. Kindly click the like button if you enjoyed the video, and ensure to subscribe and share the video so that a lot of people would benefit from it. Thank you.